leader of EuroWeb's Working Group 1, and along with my co-organizers, Hanna Lukesova, our Virtual Networking Support Manager, and Francisco Gomez, our Science Communication Coordinator, we would like to welcome you to the fourth presentation of our Advanced Analytical Techniques for Textiles workshop. During the presentation, you're welcome to write your questions or topics for discussion in the chat, and you will be invited to speak at the end. We are very thankful today to have the contribution of Sanna Lipkin, Ville, Karjalainen, and Mikko Finnilä, and I'm so sorry for the pronunciation, stick to the text, what you see written. Dr. Sanna Lipkin is Academy Research Fellow at the University of Oulu and holds the title of Docent in Textile Archaeology at the University of Turku. Her personal academic project focuses on child burials in post-medieval Finland from 16 to 1900. Additionally, she has been granted by the Academy of Finland a project for early career researchers titled Daily and Afterlife of Children from 1300 to 1900, New Perspectives in Identifying Childhood in the Past. In this project, the most challenging questions are related to the socialization of children, as well as finding children's own voices in the Finnish archaeological materials from burials and school sites, as well as probate inventories, meal and school records. These will be approached through the application of theories of emotions and performance. Bioanthropological analysis reveals the nutrition and health of children in the past, and stable isotope analysis enables discussion of breastfeeding patterns. These provide a starting point for considering past parenthood. Within this project, Sanna has collaborated with researchers from the Faculty of Medicine and the Medical Imaging Physics and Technology Research Unit. Dr. Ville Karjalainen, who is a multidisciplinary project researcher at the University of Oulu, his focus is on biomedical and archaeological micro-CT imaging applications and image analysis. And Dr. Finnilä, that gained his PhD in 2014 from the University of Oulu, his early work was related to bone toxicity of persistent organic pollutants. The work was interdisciplinary and realized as international collaboration with partners, including the Finnish Institute for Health and Welfare, Karolinska Institute and Forensic Institute at the Cranfield University. Dr. Finnilä has extensive expertise on musculoskeletal diseases and biomaterials. He is vice leader of diagnostics of osteoarthritis and is the principal scientist for microcomputed tomography facilities at the University of Oulu. He has published around 80 peer-reviewed scientific articles that have been cited over 800 times. His age index is 17. His research interests are relating to imaging and especially X-ray computed tomography, musculoskeletal diseases, and development of novel treatment options for osteoarthritis and fractures. Today, Sanna Lipkin will give us a presentation titled Micro-CT and CT Imaging of Archaeological Textiles, a common presentation with other two researchers. And at this point, we would like to invite Sanna to the virtual stand.
Thank you, Christina. It's a pleasure to be here today, and good evening to everyone. I'll start our presentation and hope it will be working okay. Today, we will talk about computed tomography scanning. I will just put the video off to make sure that the presentation works okay. We will talk about computed tomography scanning, how it works, and what benefits it may have in investigation of archaeological textiles. First, Mikko and Ville will discuss about the methodology, and later I will show a few examples of our scannings. So, Mikko.
Okay, can you hear me? If you could drop a reaction from the button, anybody?
Yes,
Thank you.
I can hear you.
Thank you. Okay, so I'm gonna review first the boring technical aspects on what is related to the computed tomography imaging. And we are mainly focused today on microcomputed tomography, where the micron refers to the resolution range. And by micron, we do not exactly mean 1 micron, but from few microns to tens of microns. And here's an image from our current facilities that we are soon gonna upgrade, but you see Sanna setting up a textile scan on her specimens, and the sample is sitting on the scanner. But how it works after that, please, next slide. So in all the computed tomography devices, you have, of course, the X-ray source, and these are greatly dependent on the type of a scanner that you have. The spot size is varying, which is related to the resolution that you can achieve with the system, and also the energy range. And typically with textiles, you prefer sticking on the medium energy ranges. But you can also see here that the X-rays are ejected from the source in this kind of a cone. And this spread allows to have magnification, so it's a geometric magnification. And that means that the resolution of the scan is related to how close you can bring your sample to the detector. Because you can imagine that closer to detector the sample is, larger the pixels are coming from the sample. And typically here the pixel intensities, they are referring to the apparent density of the material that is being reconstructed. Next slide, please. So basically this, you can start the first video. Thank you. Basically there's 3 phases when you do computed tomography or microcomputed tomography or X-ray microscopy. So first you do this kind of a scan, and these are now the projection images that you are collecting that are being collected at the detector, if you remember the previous slide. And you have to collect these projections over 180 or 360 degrees. When you use a little bit of magic of mathematics, or you do so-called back projection or Feldkamp combing method, you can calculate the cross section. So Sanna, please, second video. And here you can see the reconstructed cross sections that are being calculated from those projection images. So you calculate huge stack of a cross-sectional images from your object. And when you have the set of the cross-sectional images, you can do visualization and analysis in 3D, as shown in the last video. So if you please run it. So one can then ultimately visualize the image structures in 3D and carry out size analysis or density analysis on those objects. Next slide. I'm sorry that I had to add here a couple of slides of physics. So basically, in order that you can image textiles or any other objects, you need to have a variation in those projection images for the X-ray intensity. And you get that intensity variation if you have absorbing or your sample is absorbing part of the X-rays. And the mathematics, so the second phase is always most simplest if there's this phenomenon called photoelectric absorption occurring, which means that the full photon is absorbed by the material. So still there's just a lot of equations here, and you might ask that, well, how do I know if I can image my textiles? So the resolution comes from the absorption coefficients, and they are related to the, first of all, the material that you have, and especially on the atoms that your material is being made of. So you can see that the absorption coefficient increases dramatically when you have larger atoms. And actually at the end, they become quite soon, they absorb all the X-rays. And what you need to then do is that you have higher or harder X-rays, which means that the X-rays have a shorter wavelength. This is basically or typically given as a electron volts as an acceleration voltage in the X-ray imaging systems. Good. Next one, please. So as our title was micro CT and CT imaging, it's good to know that there's in general, there's two types of systems. So if we consider what they have in hospitals, those systems are something similar, these systems have gantry that is rotating. So the X-ray source and the detector are rotating around of the sample or patient. While these sample type of imaging devices, you have a rotational states. So your X-ray source and detector are fixed in fixed positions and your object is rotating. Next one, please. Because of the textiles are typically so-called soft materials and they don't significantly absorb, I think it's good to mention that there are more and more coming these new imaging modalities like phase contrast imaging. So what happens in the phase contrast, and this is a specific mode of phase contrast imaging called propagation-based phase contrast imaging. But if you look at the bottom, you can see that there's that red sample. And on the detector, it causes absorption that you can measure. This could be line profile. However, if you move your detector away, you start to see this kind of edge enhancement. And this edge enhancement results from the fact that the X-rays move slower in the samples, and it causes also phase difference in the X-rays. And when you place the detector far enough, there's a superposition of the X-rays, and that enhances the edges. And this is especially useful when you're imaging soft materials like textiles. Next one, please. So a little bit to summarize from the first part, the benefits of micro CT and CT imaging is that they are non-destructive analytical technique, which can provide either cross-sectional or three-dimensional information of the image object. So they're highly valuable when you're characterizing internal structures of textile fabrics. Furthermore, it's been found extremely useful or beneficial, the fact that you can view the three-dimensional images from different angles to cuttings in the orientations that you prefer. It is excellent method if you happen to have materials that have different compositions that you can visualize as a means of different densities. And as I mentioned, there are these new methods coming available for low absorbing materials. Next one. And how to choose different methodologies. So I think something that you need to remember, you can hear stories from nano-CTs or sales pitches of nano-CTs, micro-CTs, and different kind of systems. But what you need to remember is that most of these systems are still operating on basis of the geometric magnification. So if you hear that some device can produce resolution of 1 micron, it doesn't mean that you can have this 1 micron resolution with all the sample sizes. So if you have a huge sample, most likely the 1 micron resolution is not achievable. Also, like further details you want to gain if you want to image fibers. This higher resolution always takes more time and causes higher radiation dose on the samples, and especially if we are talking about samples related to cultural heritage, they are rare and should be protected. And then finally, you need to figure it out that what kind of energies or X-rays you can use. Like we have examples later that there might be nails or pins in your sample that are causing extra trouble. And although you would like to use soft X-rays, you are then forced to go with harder X-rays. I think after this we are gonna change Vipa or Ville to talk.
Yes, thank you, Mikko. Can you confirm that you can hear me?
Yes.
That's great. So I will be talking about the segmentation of the image sample. So this is after that we have done what Mikko described, that we have done the initial scanning and reconstructing of the sample. So this is part of the image analysis and processing. You can go into the next slide. So for the image segmenting, the goal is to simplify the image or remove the unwanted data, or to make the analyzing of some different compartments or some compartment to make it more easy to analyze or more visually clear. For example, in textile fabrics, we can split the data into the structural components of the weft and warp of the yarn. And while we do that, we can also remove the possible dirt or like Mikko said, these very dense hardened material from on top of the surface of the sample, so that we can study the internal structures. And I'd say it's easy to do. It's somewhat fast to do, but because the micro CT stacks can get quite big, they can have 1,000 times 1,000 pixels and then as many slices as you have. So it can be quite huge. So going through most of them manually can take time, but in that way you can get very accurate segmentation results. And of course, there are some automated segmentation, like you can pretty fast segment based on the density of the materials. If you have very dense and low density materials, you can easily segment them from each other by thresholding, but more difficult automated segmentation require more advanced software and tools. Go to the next one, please. So in the segmenting, what we are doing, we are giving each pixel a label. And in that, we mean that we split them with these labels. For example, in here, we can look at the middle image. In the red arrow shows in the image that there's black, meaning that there's low density, most likely air. And we don't really get much information from it. And then next to it is this white spot, meaning it's very dense. This is most likely some sort of dirt or patina. And I'd like to say that this is just a single cross section from this total image from the right. So the blue line is what we are looking at right now. So you can see in the right image on the surface, there's this huge white dense dirt part that's blocking most of the view. But with the micro-CT imaging, we can look past that. And at the same time, after we have removed, we know that, well, this white part is dirt and black part is air. So we can look at the more gray area and see that how the fabric is woven. So in the yellow arrow shows there's this vertical yarn going through the whole sample. From here, we can label it as the weft of the yarn. And then with the blue arrow, we can see this circular gray area with some air around it, and we can then label it as a warp. And if we do this, we can do this for the whole sample. So could you please go to the next one? Yes, we have the video. So this is going through this stack image one by one. So you can see how there's this white vertical fabrics that are the weft of the fabric. And then there are these worm-looking circular fabrics that go through with changing sides. So this is the warp going over and under the weft. And it's something that requires some perception of the 3D space and some knowledge of the sample to see, but for that we also have the 3D visualization that makes it this much easier, but the initial segmenting is done in this 2D from these 2D slices. Next slide, please. So here we have a piece that I'm presuming Sanna excavated from the area that she'll show later. And we have taken this smaller volume of interest from the middle. On the top, there's again that dense dirt part, but we won't let that bother us, and this is less than 1 centimeter times 1 centimeter, the volume of interest that we have in the orange box. So you can click. So when we have done the initial segmenting and labeling in the orange, we have taken the weft of the warp. No, wait, warp of the yarn and colored it with orange so we can nicely see it in the 3D image. Then you can click next. And from the same image, we have taken the weft and colored it with blue. And next. And when we combine these, we can see how the two yarns interact with each other and how they entwine together. The next. And here we have taken all the redundant matter that we did not want in our segmentation away, and we are just left with the weft and warp of the yarn. Next slide. So here's another example. We had the wool piece. It was the size of a coin, and we took this yellow boxed area as our volume of interest to do the segmenting. Next, please. And again, we took the weft and warp of the yarn and combined them to make this colorful image where you can easily again see how the weft and warp interact each other, how they go over and under each other. And in the last image, you can see the comparison of what we see without the segmentation, what we see with the segmentation. So we have gotten rid of a lot of the dirt that was on top of the sample, and that made the visual analyzing of this sample difficult. Next, please. And now it's Sanna's part, and so I leave it to you.
Okay, thank you both Mikko and Ville. I will first talk about scanning coffins and later come back to the micro-CD image textiles. In Oulu, we have CT scanned altogether 8 coffins, and the CT scannings have been taken at the University Hospital. 5 of the coffins are currently in situ at the old medieval church at Keminmaa. Oops. I suppose the map isn't here, but you will see the location later. There are 4 infants CT scanned from here and 1 adult. In other church from Haukipudas, which is a bit north from Oulu, we have also CT scanned 3 coffins of newborns. Today, I'll show a few images that will demonstrate how CT scanning can be beneficial in order to study coffins and coffin textiles. Images are reproduced with Osiris software that can be also downloaded for free from the website. This coffin belongs to an infant that was mummified. She was 3 to 6 months of age. Actually, I'm missing one picture, but it doesn't matter. Here are 3 cross sections from exactly the same location within the stack of images. Here you can see inside of the infant skull, there is some dirt in the skull. Inside the skull, you can see the coffin, the cross section of the coffin, and layers of textiles, and both hands into images. Here is from the same coffin, the feet area, again with layers of textiles, and the mattress layer here below. Can you see the arrow right now? Should I draw here? Here is the layer of birch bark that was a mattress for this burial. Here's another set of images that kind of shows you how the CT scanning, reconstruction CT scanning works. CT scanning is adequate for viewing how textiles are placed in the burials and for general observations on different densities of fabrics, but not enough for study of textile structures, for which you should use micro CT scanning. In these images, it becomes obvious how viewing with Oserix allows identification of materials with different densities. Window length and width, that is upper and lower boundaries for material density selected for viewing, can be adjusted to illustrate both dense and lighter substances. Here you can see in this picture on the left side, you can see the denser materials that are bones, but on the right-hand side, you can see also the softer materials, the textiles. And what is interesting in these pictures is that the girl is holding base for a floral accessory in her hand that is totally, it's not visible in if you look the coffin in real life, because it's hidden inside her palm. On this left hand side image, you can see the surface of the skull, but once we are adjusting this window length, we will get to see also the textile on her head. And in the last picture, you can see also the embroidery quite nicely. In the picture, there are also these seeds here. They are birch cherry pits that are brought to the coffin by a rodent. There's a birch cherry growing, several birch cherries growing on the churchyard. Here you can see that seams and the places where there are 2 layers of textiles are quite easy to view on these images. The problem is with these CT scannings is that many textiles are very light, and the closer we get to the density of air, the more invisible the lightest textiles remain. The cap of the infant's head is made from tulle, and whereas the floral decoration and the embroidered dots are easily visible, the tulle itself remains mostly invisible. It's difficult to kind of get to see it on these images. Here, I tried to make visible the silk fabric on the infant. On the left-hand side, you can barely see the plates on the textile, where you can see the bones of the infant. But on the right-hand side, you can see the textiles better. And what is important are here the figures of window length and width. So it's kind of playing with these figures, trying to find a good combination of those. In the picture, you can see also here, lace that encircles the pillowcase of this child. So you can kind of see all the textiles on top of each other, and you can see through them. So basically this lace is underneath the child, but you can also see the textiles on the child with the same view. Here in her feet, there's something on her feet, but on the left-hand side figure over here, you can see that it is on a layer of textile. So it is not directly on her feet. Here you can see also the veins of the child and a really nice pin in the lower part of the picture. Here I have already adjusted the viewing. These images tell me that the infant is not wearing any stockings, and silk fabric and the tulle that cover the body are not visible here because they are lighter than the other textiles visible here. Under the body, there are two layers of fabrics. One covers the mattress, and the other is placed here, undulating, kind of undulating below the body. There's also one fabric with seams over here that is above the ankles of this infant. Okay, and this is the first research that we have published so far, considering the CT scannings we have made. Again, we will go back to micro CT scanning. The examples that we have micro CT scanned have been found at the late medieval church site of Valmarinniemi in northern Finland. Okay, over here. And actually the Kemimaa church is located where the previous coffin was found. is located at the same location as Valmarin, or very close to one another. But there was also, there was this slide first. So what kind of textiles are suitable for CT scanning? The most suitable are the ones that don't contain any metal, which can be problematic, as Mikko said. The smaller, the easier it is to get proper imaging and nicer outcome. And the items cannot be too fragile. Okay, so let's go back to Valmarinniemi. The preserved textiles were found associated with metal objects, and most of them date to the 14th century. Here we have a tablet woven band attached to spiral tubes. Let's put the video on. Oops. I have the pen on. So this is very small item, as you can see, and it was really difficult to study based on photos. As you can see, the spirals are very nice, but the metal on this causes streak on the surface. So it's almost impossible to see the actual textile on this picture, but you can see the metal easily. Okay, and then the other video. And here is the tablet woven part of this object. There are two very tiny pieces of tablet woven band. And based on these micro CT scannings, we could see that they have a tubular edge. And here you can see the diagonal pattern that starts to take shape more easily here than based on the photographs. In this case, a clear advantage of this micro CT images is to see the state of the preservation of the threads. We can see that web thread is completely invisible at times. And of course, it is mostly invisible on the surface of the textile. And with CT scanning, we can see how it kind of travels inside the textile. Clearing dirt and corrosion products off and segmenting individual threads provides a clear image that can be used while studying the weave patterns and how individual threads twist around each other in this tablet woven band inside the textile. And here you can see amazing job that Ville has done with while segmenting the yarns here. I personally just I'm always as much as amazed about these pictures every time I see them. How nicely these work. Micro CT imaging and segmentation made it substantially easier to understand the tiny piece of tablet woven fabrics. Together with microscopic viewing, it was possible to reconstruct the colors used and the pattern and how individual tablets were turned around while this tablet woven band was made. And together with Hanna Puolakka, we were also able to understand the nature of the finding of this find and look for possibilities for its geographical origin that point to the east, possibly to Karelia. Here is the other example that also Ville was showing pictures of. It's the oldest piece of cotton from Finland, plain woven piece of fabric from early 14th century. And here we can see again Ville's amazing videos. You can see how there is dirt on the surface, but with segmentation, we can see the spin directions of these yarns. And of course, the structure, which is quite easy here. And once we get closer, we will see also this item on fiber scale. To analyze fibers, we will need to have a different kind of CT scanner. Here, this is a piece of fallen off. This piece was found from the box in which the fabric was stored, and it was nano CT scanned with the precision of 700 nanometer voxel in size, and it is possible to study the fiber features, and through segmenting it's easy to study individual fibers. From these images, we can see the C-shaped structure of cotton fiber and how the fiber twists around itself. In the images, 12 individual fibers were segmented, and through segmentation, we could select the fibers that were best preserved, which allowed the best options for the analysis of the thickness and of their shape. But I'm trying to stop the video. Okay, so this was our contribution for today, and we are of course open for questions and comments.
Thank you very much for this fascinating presentation. Let me see in the chat. Well, one thing, one question is, when you mentioned about the wavelengths and wave widths, if I'm not mistaken, that were different for you to be able to make an image of the different textiles in the coffin with the infant. Is this something one needs to set up when they're actually doing the CT scanning? So you need to do multiple scans with different settings. When do you choose these?
Son, do you want that I take this?
Yes, I think you have more.
Yes, there's two questions combined, if I fully understood.
Okay.
your question was related to the coffins, and Sanna was talking about the windowing that allowed you to visualize certain type of structures at one go. So you can do that windowing to any kind of computed tomography images, and basically if we remind ourselves the fabric sample that Ville was showing with the patina on top. So basically you could do the windowing so that you only saw the patina part, or that you saw greater density difference between the yarns. Because you could see some kind of a grayscale variation. However, depending what kind of a windowing you have, the difference they might look, all the yarns might look the same, or they might look different. And for that reason, it's important to select the windowing properly. However, the energies then what you use for imaging, that kind of gives you the basis. For example, if you use very hard X-rays, so high KVs, when you do the imaging, you see less of these soft structures. So you at some point you lose those soft structures totally.
Yeah, and I think in this case, the original idea was to see the bones. So perhaps they chose something that was not that beneficial regarding my interests.
But this is something that is set during the scanning, right?
Yeah, and I mean, I have understood that with these medical scanners, you can also affect on the resolution. So you can, for instance, the teeth area of this infant was scanned with a greater resolution than the other areas. So that is also possible with.
We have another question. It's from Jane Malcolm Davis. She said, I did some CT scanning of a knitted fabric and found that it is possible to use time lapse to measure the depth of the nap on the surface. Do you see other ways of calibrating the characteristics of the textiles? And please, Jane, open your microphone if you want to add something or
Yes, so dynamic CT imaging is coming with the faster devices. I'm not able to fully get the exact question. So what kind of a time lapse what was it that was performed?
So I had a sample of modern fabric which had a nap on it, and the CT scan effectively scraped away the nap from the surface of the fabric, so you could see the knitted structure underneath. And the person I worked with at DTU in Copenhagen suggested we could find a way of calibrating the animation so that we could count the seconds that passed as the nap was scraped away, and that would allow us to calculate the depth of the nap. So I'm thinking also about other ways of measuring, for example, the number of threads in the warp and the weft, which you could do without the need for the animation. Did you think about maybe how you could automate some of that kind of counting?
There's numerous ways. With the time of the digitalization, everybody is speaking about deep learning based reconstructions that have been also used to kind of reveal, for example, text on on difficult archaeological samples, and we haven't done quantitative analysis, but basically if you combine a lot of these automated segmentation means, there's a lot of like numerical tools that you can apply to get the orientation, size of the yarns, and etc. I'm not sure if I'm getting towards the answer that you are.
Yeah, I think this is very exciting because a lot of these things are very difficult to count, even under a good microscope. To count and measure these things in these ways provides us with a much more accurate way of understanding the structure and the construction of the textiles. So I think this is a very, very fruitful area of investigation, and especially the prospect of automating some of this calibration, which would be excellent.
Yes.
Yes, I completely agree with Jane, because although sometimes it might seem very straightforward, even wind count is not at all easy with excavated textiles. So I think this is a fantastic potential of this technique. And I wanted to, yes, I just see a question. I also had a similar question, because you said that one of the problems might be the presence of metal. What about if that is metal degradation products impregnating the textile, a mineralized textile? Would that create a problem with CT scanning?
Yes and no. Like in our case, I think it was copper. Can you confirm that? Yes. And copper is heavily absorbing material. It causes some difference, but it's not as problematic as those rolls, or what are they, Sanna?
The spirals.
Spirals. Yeah, imaging textile next to those large spirals, that's really challenging at the moment. But if structure is mineralized or oxidized, or if there's some metals, but the structures are still intact, it should be okay for the image.
Oh, that's it. That's good then. So because I wanted also to ask about the spirals. So you wouldn't be able to see any textile, any threads inside the spirals? Or what if the spirals were metal threads that are much smaller? Would we be able to see any fibers inside the metal threads?
In this case, there were threads, and they were visible in I just cut out this this part of the when the video went inside the spirals. There was thread, but I think it might have been oxidized inside there, so mineralized. I mean, so it probably wasn't yarn anymore.
So in a way, more similar in terms of absorbency to the spiral itself.
Yes,
so basically the problem is that you want to use those soft X-rays to image the fabric structures. And when you have the metallic frame, first, and in general, it's monochromatic. So you have all kind of energies in the X-ray beam. But what is producing the contrast in the images are those softer X-rays. But however, when those soft X-rays are interacting with the metal, they are first absorbed. So what you have left that go through the whole structure are those hard X-rays, and they produce less contrast variation for fabrics inside the metallic structures, and they are hard to see for that reason. I don't know how the situation would be with more powerful systems. It's quite like medium performance system that what we have at the moment in the lab. So if we would use like more state-of-the-art imaging devices, that would they then be visible, perhaps.
Mm-hmm. And a more practical question, because when we're talking about excavated textiles that are very fragile and they would probably need to be supported all the time by a mount or something with that, I guess that would also be visible. Is this something that you can delete in, again, as you do with the air and the dirt?
We used dental bags to support the textiles, and of course it's possible to delete from the images. It's always possible to cut things out.
That's really useful. What about consolidants? Have you had any experience with CT scanning consolidated textiles in the past?
Yes, yeah, the one with the spirals, it had solidants.
Okay,
but we didn't see the textile in the images. So, well,
maybe this was also one of the reasons why.
Yes, yeah, that could be. That would be, yes.
Are there any more questions to our speakers? I don't see any more questions in our chat, so I think this is the time to thank you all very, very much for doing this presentation for us. It has been very interesting, and thank you everybody for attending our workshop today. Thank you.
Thank you.
Thank you.